So in this mini lecture, we work through how you would actually calculate PCA just using the raw matrix algebra manipulations in R without having to type print comp. This is an optional lecture. Again, if there was a final in this class, you wouldn't be responsible for this. But it's sort of interesting to see what's happening, and I think it helps you really understand what PCA is doing to work through just a little bit of the math of how it's done. So let's return to our Gala data. Again, if this faraway isn't loading for you, you have to do install.packages faraway. So you have to, faraway is not part of base R. So you would do install.packages faraway, and then you would say library faraway data Gala. So this again comes back to our Galapagos island. And again, the first thing that we do is we just mean subtract the column, so that will match up the mathematical normalization that we're doing here with the normalization that the PCA or the printcom function does in R. So we start with our mean subtracted columns. Then we form a covariance matrix. So you guys will remember from your first semester stats class that if variance is this familiar form of xi minus x average squared divided by n minus 1, the covariance between two different vectors is xi minus x average squared times yi minus y average squared, right? So it's like instead of variance, it's covariance. Of course, if the two vectors are the same, then the covariance is the variance. So we form a matrix where we compare, so for example, if we had three vectors, we would compare each of the three vectors all the possible ways, right? So we would compare each vector to itself, and that would be the diagonal. So the diagonal of the covariance matrix is the variance. And then on the off diagonal of the matrix, we would have the covariance. So we would compare, for example, x to y here and y to x here. Right, so this will give us a 3x3 matrix if we have three vectors, importantly, this matrix is symmetrical, right? That the covariance of xy is the same as the covariance yx, right? Again, the properties of this covariance matrix on the diagonal, diagonal is the variance, and this matrix is symmetrical because the covariance of xy equals the covariance of yx. And we'll see actually that PCA can be done on any symmetrical matrix. So you can use, if you didn't want to use covariance, you could use another distance metric to compare two vectors. And we'll see that with Bray-Curtis dissimilarity, which is often used for metagenomic data, for performing PCA metagenomic data. And we'll see that in the next mini lecture. Okay, so R makes this super easy for us. We could manually get this covariance matrix, but to get the covariance matrix in R, all we have to do is say COV. So this is the covariance matrix. So there's seven. Remember, we have 7 columns of data here: species, endemics, area, elevation, nearest, Santa Cruz, and adjacent. So each column of so along the diagonal is just the variance of each one of our 7 columns of data, and the diagonals compares the covariance comparing any two columns of our data, right? So all we have to do in order to get this covariance in our covariance matrix in R is to type COV, and just to prove that that these numbers are what I'm saying they are, right? The variance of the first column, right? I could get that here. Give me the variance of the first column, and that's this, or give me the covariance of the first and the second column, and that's that number. So that just proves that that this covariance matrix is the way that I've defined it. Okay, next we have to form the eigenvectors and eigenvalues of the covariance matrix. So obviously you would spend, if you take a linear algebra class, you could spend a couple weeks learning how to do eigenvalues and eigenvectors. If you've done any kind of physics, especially quantum mechanics, you spent a lot of time doing eigenvectors and eigenvalues. So here I'll give you a 15-second summary, which obviously if you want more information, you need to go to another class. But the basic idea is that you have some matrix that you're trying to represent, find the eigenvalues and eigenvectors of. So the basic idea is that you're going to try and find starting with this matrix, which we'll call A here. We're going to try and find eigenvectors, which we're calling X. And the basic idea is that you can take this eigenvector and multiply it by a scalar here, and that when you do that, you would get the same result as multiplying the matrix times the eigenvector itself. So we can represent this. Multiplication of the matrix that we're starting with times the eigenvector is going to be the same thing as this scalar times the eigenvector. Now, again, if you've never seen this before, this isn't going to make any sense to you whatsoever, and obviously, you need to go to another class to learn lots and more about these. And it's outside of the scope of the class this class to go into much details of this. So it turns out that eigenvectors and eigenvalues have these incredibly useful properties. And so if you have a square matrix, and you can only define eigenvectors for a square matrix. So it turns out that there are, if you have an n by n matrix, there are 3 eigenvectors. So if you have a 3 by 3 matrix, there are 3 eigenvectors. And if that matrix that you're starting with is symmetric, right? And remember, the covariance matrix is symmetric because this value equals that value, and this value equals that value. So the symmetric means that if you kind of you have this upper triangle, if you kind of flip it to the lower triangle, the upper triangle and the lower triangle are the same thing, right? So if this eigenvalue is symmetric, then it's going to turn out that the eigenvectors, and this is actually a fairly easy proof to go through, although we're not going to go through it now. So we'll say smart people tell us, but it's not that complicated a proof to show, although it's outside the scope of this class. So it turns out that the eigenvectors of a symmetric matrix are perpendicular to each other, no matter how many dimensions you have. And so this symmetric matrix is an example of Hermitian matrix. A Hermitian matrix is one in which the conjugate transpose of when you see the conjugate transpose of a matrix, it's identical. Since there are no complex numbers here, the conjugate doesn't matter. So we can think of a symmetric matrix as one where you transpose it, you get the same matrix, right? So if I transpose this matrix, if I switch the rows and the columns, I get exactly the same matrix because the diagonal is the same, and I switch the rows and the columns, and those are the same too. Those are the same too. So it's going to turn out that the eigenvectors of a symmetric matrix are perpendicular to each other, which again, fairly easy proof to go through, but we won't do it here. And the eigenvalues are going to turn out to be real. That's going to be important because the eigenvalues are going to be used to tell us to give us a quick way to calculate the proportion of variance that each axis explains. Okay, so again, to go back to our homemade PCA here, so I have my covariance matrix, and then I can get the eigenvalues and eigenvectors in R by just typing eigen covagala, right? So this is the covariance matrix of my original data, right? The variance along the diagonals, the covariance off the diagonals, and I say eigen covagala, and I get the eigenvalues and the eigenvectors, right? And the idea of these eigenvectors is that there's some 7-dimensional space that they represent, and each one of these vectors are orthogonal to each other, right? So if you take any one of these vectors and do matrix multiplication against any of the other vectors, that comes out to 0, which is to say, in the 7-dimensional space, they're at right angles to each other. Okay. So then to get the principal components, right, this 7-dimensional space, so to come back to the idea of our linear models, because these vectors are orthogonal to each other, right, when we rotate our data onto the 7-dimensional space, we're guaranteed, we're guaranteed not to have correlated input variables into our linear models. That's the whole reason we're doing this, right, is to make sure that we don't have, we're compressing away, we're doing data compression to compress away the redundant variables. Because the variables are going to be orthogonal to each other, they won't introduce numerical stability into our models, which is what we want. So all we have to do to get the principal components then is to take our original data, or our mean subtracted data, and then we just do matrix multiplication to rotate this data into this new orthogonal basis, and then we get our principal components. Okay, so that's a fair amount of typing that I had to do, right? So again, to review these steps, I have my mean subtracted, right? I start with my mean subtracted data here, right? So I have my mean subtracted original data. I form the covariance matrix here. I get the eigenvalues of that covariance matrix. And then I rotate to get my principal components. I take my original data and I rotate it onto this new orthonormal basis, which gives me the eigenvalues of my this new orthonormal. Wait, when I rotate my data onto the eigenvalues of my covariance matrix, which forms an orthonormal basis, I get my principal components. So that's a fair amount of typing, right? And so just memorize these numbers, 332, 89, 440, right, just to show that they're the same here. Or with much less typing, I can take the original data and just say print comp, gala, scores, and that's how I get my principal components. Now, The percent variance. So remember, the percent variance here is a measure of how much correlation there is in the original data matrix, right? So we saw, like, again, we were thinking about this, right? If I stored all seven of my original columns in this one principal component, when I uncompress it, how much of the original data would I get back? And that answer is going to be 60%, right? And if I had the second component here. So if I used two columns, if I use these first two columns to store the original 7 columns of data, how much of the data would I get back? And that turns out to be 97%, right? So it's going to turn out that that a way that you can calculate this cumulative proportion very quickly without having to uncompress the data is it's going to turn out that this first component, if you take the first eigenvalue that's associated with the eigenvector and divide that by the sum of all of the eigenvalues, that number turns out to be equal to the proportion of that's explained by the first component, right? And then if you take the first two, you get the percent value, the percent of the data that's explained by the first two components, right? So so this is vector in, vector out, right? So I take each of these eigenvalues and then I sum them by the I divide that by the sum of all the eigenvalues, right? And this first number is 60.2%. So my first component explains 60.2%, and the second component explains 36%, and the third component explains only 2.6%, right? So these numbers here I get by just taking each one of the eigenvalues and dividing it by the sum of all the eigenvalues. Now just to think about it, to give you guys one more visualization. So again, that math, if you've never been exposed to linear algebra and you've never heard of eigenvector before, that math is not going to make a ton of sense to you. But just to give you one more visualization about what the PCA ordination is doing, consider just a simulated data set here, right? So I just have this simulated data set, two things that are more or less correlated with each other with some noise added, and I just have like red and blue, right? So this is just two pieces of data, right? Weight of the mouse, age of the mouse, whatever, right? Two pieces of data here, right? So what the principal component is going to do is it's going to rotate this data until it finds an axis, or so that it finds an axis which explains most of this data, right? So this first axis doesn't explain much of this data here, right? So if I just consider this first axis here, right? If I draw just a line parallel to this data, right? I'm not capturing very much of the data here, and I'm not capturing very much of the data here. Now I'm free to rotate over any basis that I want to, right? So so there's lots of bases that I could rotate on. So this is a basis here that just flips the data, right? But flipping the data doesn't really help me very much with this first principal component, right? With this first axis here, right? When I flip the data perfectly, I'm not really explaining any more of the data on this basis versus the other basis. But here, right, in this third plot here, I've used the principal component to rotate the data. So yes, right. So in this first plot, we just rotate the data by any old basis, right? And that just flips the data here. So here, a basis is just some random basis that we've defined here that flips the data, right? So that doesn't do us much good. But when we choose a basis that is the eigenvalues of the covariance matrix, right? So here I form the covariance matrix. I form the covariance matrix here, and then I choose the basis that is the eigenvalues of that covariance matrix. Now I've rotated the data so that along this x-axis I explain most of the data, right? So if I draw the median line here, right, that again, this is the guarantee that's been made. There's no rotation of the data, which is going to explain more of the data along this first axis, and you can really see that here. And having done that, now I could do inference, for example. So here it's not necessarily clear how I do inference on the red versus the blue dots, but here once I've done this, once I've rotated to this space where we're all aligned along the x-axis, when I do inference on the red versus the blue dots, right, I can just look at PCA1 here and see if the red dots are different than the blue dots, right? So I can do my PCA print comp data, right? This first principal component explains 95% of the data. There's no better rotation, right? You're not going to be able to rotate the data any better than we've rotated it, right? So we get the most explanation along this first axis. And then, for example, I can do a Wilcoxon test comparing PCA score along this first principal component. I can compare the red versus the blue dots here, right, and do inference and get a really small p-value, because obviously the red dots and blue dots are different, right? So I've kind of I've rotated the data into this new coordinate space, and in this new coordinate space, I can do this really nice inference because the only thing that I care about, right? I've taken what was a two-dimensional data set, and reduced it to a one-dimensional data set. That one-dimensional data set captures 95% of the information that was in the two-dimensional data set. And so when I do inference in this one-dimensional space, I can use the Wilcoxon test. And in this one-dimensional space, my Wilcoxon test maintains most of its power because I've explained 95% of the data that was in the original two-dimensional space. So this is obviously not something you'll need for the final. There's lots of really great stuff in this first chapter. This is my favorite treatment of sort of basic linear algebra, is in the first chapter of the Shankar book, the Principles of Quantum Mechanics, including proofs of things like that eigenvectors of Hermitian matrices are orthogonal for an orthogonal basis. So there's really nice proof of that in this book if you're interested. And likewise, here for your reference, not going to go over it in the YouTube video, but if you ever need to implement all of this in Java, there's instructions for how you would do that as well.